This is ELC 131, Circuit Analysis 1, and today we're going to talk about losses in electromagnetic systems. Now, there's four major or main sources for losses in an electromagnetic system, and I have them listed in terms of the magnitude of the losses in the system. And the first source of losses is what's called winding resistance or copper losses. And of course, we look at a simple electromagnet, and when we apply a voltage source to the winding, of course, current's going to flow through the winding. And anytime we have current flow through a resistance, we're going to have power loss or power dissipated in the form of heat. Now, the resistance of this winding can be a few ohms, but it can also be more than 100 ohms, depending, of course, on the length of wire and the cross-sectional area or the diameter or the wire gauge. So, again, when we have current flow, we're going to dissipate power, and this power is dissipated in the form of heat. And this loss, again, in the form of heat, will represent itself as a loss between the current that flows and the magnetic flux that is created. Now, our second largest loss in magnetic systems is due to what is called hysteresis. And a lot of people simply refer to this as or graphically is represented as the BH curve. And hysteresis is merely a time lag between the magnetizing force, H, and the flux density, beta. Now, hysteresis only occurs when the source to the electromagnet is alternating current. And again, I have sketched the sine wave that represents the source voltage and the resultant current through this winding. So this is a sinusoidal AC source. Now, looking at this AC waveform, understand that we start here when the source voltage is 0 volts. And of course, the current increases in a positive direction. And on our graph, this will be represented as positive H. Now again, H equals ampere turns per meter, and current can either flow in this direction when it's positive, or current can flow in this direction when the source voltage is negative. So we have to, on the horizontal axis, the x-axis of our graph, have positive H for current flowing this way and negative H for current flowing this way. Now, when current flows, we're going to create a magnetic field inside the core. And this magnetic field will have a north to south, or have north to south poles as shown, because of the direction of windings, the direction of current. Remember the right-hand rule, we wrap our fingers around the winding or the coil in the direction of the windings. Our thumb points to the North Pole. Now, as this source voltage and current increase, this magnetic field is going to expand. So as current increases in the positive direction from here to here, we'll see that the flux will increase also in a linear fashion. However, if you recall from the previous video when we talked about ferromagnetic material and iron in particular, remember that when iron is placed in proximity of flux, a d orbital electron from a lower subshell is pulled up into the valence shell. Its magnetic moment adds to the magnetic moment in the valence shell, and that's why iron is magnetized. But if we keep increasing current, then we reach a point where we simply cannot pull up any more d orbital electrons because they're all pulled up. And we find that we reach a point of saturation. And all this means is that regardless of whether or not we increase current, the magnetic flux simply cannot increase anymore because we've run out of atoms to be affected by the flux. Now, from the peak point back towards zero, understand that, of course, the current is going to get smaller and the magnetic field is going to collapse or get smaller. So as current goes back towards zero, the magnetic flux will get smaller. But what happens on this graph is even when we reach the point where the current is zero, there's a slight amount of magnetic field left north to south. And this is termed retentivity. Means that some of the flux is retained in the positive to negative direction because some of those pesky little orbital electrons have stayed out in the outer orbit. They haven't fallen back to the lower subshell. So even though the current is zero, there's still a magnetic field north to south. And again, on our graph, since our magnetic field can either be north to south or south to north, depending upon the direction of current, on the y-axis, we have to have positive beta representing a north to south field and a negative beta representing a south to north field. So we start in the negative half cycle of this AC waveform. Of course, now current is going to flow in this direction. The field changes from north to south to north because, again, now current's flowing this way. Current's flowing this way. So the North Pole will be down here and the South Pole will be up here. Now, we actually have to have some current flowing in the opposite direction before the magnetic flux goes back to zero. In other words, we have to be about here on the sine wave. Current has to actually be flowing in the opposite direction before I can force all those d orbital electrons back to their lower subshell. As I keep increasing current in the negative direction, if you will, of course, magnetic flux will increase and again reach the point of saturation, meaning that it doesn't matter if I keep increasing current in the negative direction, the flux can only get so big because there's only so many atoms for d orbital electrons to be pulled up in. Now, I start decreasing the current in the negative direction, or decreasing the negative voltage, and of course this magnetic flux is going to collapse again, and the flux will get smaller. But even when I'm here at zero, there'll be a slight amount of magnetic flux retained with a polarity of south to north. Again, this is because a few of those d orbital electrons have stayed in their outer orbit. And I actually have to increase current in the positive direction before this magnetic field goes away. Now, if I keep increasing in the positive direction here, we'll fall back into this same curve. I operate on that curve right there only the first time I apply energy to the magnetic system. Every other time, our system is going to operate on this outer portion. And because there's a difference between flux from here to here, or from magnetizing force from here to here, that represents a loss in the magnetic system. And this loss is exhibited as heat. So again, hysteresis is merely a time lag between the magnetizing force, H, and the flux density, beta. Now, the third source of losses in an electromagnet are due to what's called eddy currents. And we'll go back to what we talked about in the previous video. And remember that when I have flux existing and I move a conductor through that flux, I will induce a voltage in that conductor. And if there's a path or closed loop, I'll have current. As you hopefully understand by now, if I have voltage and there's a path or closed loop, we'll have current. So what happens is, in this system, that when I have a magnetic field inside this core, and this magnetic field expands, we have the same thing we have here. We have relative motion between flux and a conductor. So as the current increases and the magnetic field expands, we have relative motion between a conductor, the iron core, and the flux. So this motion between the flux and the conductor, the iron core, will cause or create a current that flows around this iron core. So we've got a current that's moving around the iron core like this, and it, of course, is perpendicular to the direction of the flux that is creating this current. And that's why they call these eddy currents. Eddy is like when water flows through a stream or a brook, and it goes around a branch and causes the water to go in a little circle. That's called an eddy current, or an eddy. So since these currents are going circular around this core material, they call them eddy currents. And anytime we have current through a resistive material, we're going to have what? we're going to have power dissipation in the form of heat. And again, anytime I lose power in this system in the form of heat, then it represents, of course, a loss in our magnetic system. Now, the fourth source of losses in our magnetic system is due to flux leakage. And this simply means that not all the flux created by current flow through the coil will stay inside the core. That some of this flux will go outside the core material. Therefore, it's not cutting through the conductors. Now, the losses respect to magnitude that are due to flux leakage is determined mainly by the construction of the core material. Is the core a cylinder? Is the core a toroid, which is like a bagel, or is the core material rectangular? These magnetic lines of force that we've talked about don't like to turn 90-degree corners. That's why a toroid, again, the shape of a bagel or a donut, is our most efficient magnetic system because the lines of force easily stay within that circular material. So again, our source of losses in terms of magnitude are due to wire resistance or copper losses. They're due to hysteresis, which again is simply a time lag between the magnetizing force and the flux density. Eddy currents, again, are currents that flow around the core material due to expanding and or contracting magnetic fields, and also due to flux leakage.